Hello, welcome to Forest Learn. This video is about the principle of superposition. When two or more waves meet, interesting things can happen, and the principle of superposition explains what goes on. So let's take a look at an example of this. Here I've paused two waves or wave pulses that are moving. So this triangular wave here is moving to the right, and this one over here is moving to the left. They have exactly the same shape as each other. So let's see what happens as these waves start moving. Notice that the waves appear to be doing their own thing before and after they meet, which is to say they're moving left or right with a fixed triangular shape or profile. It's only when the waves meet that we no longer see two distinct triangular shapes. In fact, it turns out that throughout, the waves are just doing their own thing, and that's even when the waves are meeting. So let's try to better understand what's going on by first discussing the principle of superposition, which fundamentally explains everything that we see here. So the principle of superposition states that when two or more waves meet, the total displacement at a point is equal to the vector sum of the individual displacements of the waves at that point. So let's unravel this and see what this means in the context of the example we've just been looking at. So here you can see a diagram of the two triangular waves that we were looking at in the simulation a moment or two ago. The blue one moving to the right and the orange one moving to the left. And you can see that the waves are just, have just started to overlap. Okay, so let's see what the principle of superposition tells us about what the total displacement will be, given that we know the individual displacements of the two waves. So let's pick a point. Let's pick this point here, call it x. And at this point x, we can see that the displacement corresponding to the orange wave is 0. And the displacement at x of the blue wave is a. So to work out the total displacement, we simply add these individual displacements of a and 0 to get a total or net displacement of a. So this is at position x. Now let's do exactly the same thing at this position here, call it y. You can see here it's quite simple. The displacements of both waves, blue and orange at point y, are 0. So 0 plus 0 is 0. So we can say at y, the displacement is 0. Let's pick one last point here, call it z. And at z, you can see the displacement of the orange wave is something like a over 2, okay, so half a, but the displacement of the blue wave is 0. And again, we just add those individual displacements to get us a displacement of half a, so somewhere around here. So if you do this, if you keep on doing this for all points running along this axis here, you can build up what the total displacement will look like, and you can probably see that it's pretty simple. If we fill in all the points and join them all up, we will get a total or net displacement that looks like this. Now recall that when we were looking at the simulation of the waves meeting, I mentioned that the waves are just doing their own thing throughout. So what that means is that a short time on from this position here, the blue wave will have moved a bit to the right and the orange wave will have moved a bit to the left. So a short time later they might be overlapping like this. And again, to work out the actual picture we would see with our eyes, i.e. to work out the total displacement, we again just have to use the principle of superposition. So as before, if I call this point x here, and the displacement of the orange one is 0, and the displacement of the blue one is a, capital A, well, then at point x, the total displacement again is just going to be a. Now let's call this point here where the blue and orange lines intersect, y. And you can see at y, the displacement of both waves is a over 2. And again, if we just add those displacements together, we're going to get a total displacement of a. So at point y, the displacement is exactly the same as at point x. Now what about at a point slightly to the right of y, say around here? Let's call it point z again. So at point z, we can see that the displacement of the blue wave is a bit less than a over 2. Maybe it's around a quarter a. And on the other hand, at z, the displacement of the orange wave will be bigger than a over 2. In fact, it will be 3/4 of a. Okay, so if the displacement of the blue wave at z is a quarter a, this will be 3/4 of a. And that's because, remember, these two shapes are identical, and due to the symmetry that we have here, if that's a quarter a, this will be 3/4 a. So again, we just add those together to give us a displacement of a, once again, at point z. And once again, if you keep on doing this for all points along this axis, and you work out all these total displacements and join them up, we'll find that the total displacement looks something like that. Okay, so you see here in this portion here, in between this point here, this corresponding to the peak here and the peak over here, in this section here, the individual displacements add up to give this sort of plateau here of displacement A. Now remember, the individual waves, they continue to do their own thing, right? So the blue one continues moving to the right and the orange one to the left. And after a short time, they will be completely on top of each other, right? So you can see that they are overlapping here. I've left a little bit of a gap between the two profiles just so we can see them apart, right? And to work out the total displacement now, it's very straightforward, because we know that that at each point we choose to examine, so for example point x here, the total displacement is just going to be double the individual displacement of any one wave, right? Because they both have the same displacement at that point. And in particular at this point here, where we have the two crests or peaks meeting, the total displacement will be twice a, the maximum displacement of either wave. So the total displacement will look something like this. It will just look like a bigger version, a stretched or magnified version of one of the individual wave patterns or profiles. So this is an important concept. What we're seeing here is that when a crest or a peak meets another crest, we say that the waves reinforce. Now here's a question for you. Once the waves have moved on further, so that the orange one is to the left of the blue one, there'll come a time when they overlap in this fashion. And you can see at this point here, where the lines overlap, the displacement is a quarter a. I'd like you to have a think about what the total displacement would be at this point in time. So please pause the video and try to figure this out for yourself. Okay, so hopefully you got something like this. At this point here, where the displacements are a quarter A, of course the total displacement there will just be A over 2, half A, right? And similar to what we were saying earlier, if we look at a point slightly to the right of that intersection point, okay, the displacement of the orange wave has gone down a bit, and the displacement of the blue wave has gone up a bit, but those changes, the decrease and the increase, they perfectly balance out, right? Because of the symmetrical nature of these wave patterns. So again, at this point here, the total displacement will again be A over 2. So we have this little region again, a little plateau type region, okay, and corresponding to this region over here. You may find it useful to go back to earlier in the video, around the 30-second mark, and check the simulation that we saw there with the total displacements that we've just been figuring out here and on the previous pages. Now here's another example. Here we have again two identical wave patterns or profiles moving towards each other. Again, what I'd like you to do is to have a think about what the total displacement would look like when these two waves eventually meet. Alright, so please pause the video and have a think about that. Okay, so hopefully you will have noticed that what we're looking at here is pretty similar to what we've been looking at so far in this video. The only difference is that these waves, or these wave patterns, are just reflections of the original wave patterns we were looking at, right? So the original ones have just been reflected along this equilibrium line here to give us these ones here. So that means that the displacements that we're dealing with here are negative instead of positive. Remember, displacement is a vector quantity, meaning that it can be positive or negative. So if the equilibrium line here, or position, corresponds to zero displacement, so for example if this green particle here has zero displacement, any particle which lies below the line, so for example this one here, will have negative displacement. But in terms of how we deal with these negative displacements in figuring out the total displacement, it's again the principle of superposition that's going to tell us what happens. So let's have a look at what indeed happens when these waves meet. So hopefully what we just saw there matches with the displacements you figured out. Now I'd like to point out that when the two waves or wave pulses are right on top of each other, so remember this idea that the waves are just doing their own thing throughout, and at some point they'll be right on top of each other, right? So again, as before, I've just left a little gap here so that you can see the waves apart. When they're right on top of each other like here, of course their displacement at any particular point, for example here, will just be the same, right? So if the displacement at this point here for both waves is minus a half A, right, then by the principle of superposition, if we add those two displacements, right, we'll get a net displacement of minus A, which will correspond to, for example, here, right? And similarly, if we were to look at the net displacement at this point here, well, the individual displacements are negative A, and so the total displacement will of course be minus 2A. So what we're seeing here is again another example of the waves reinforcing, right? So previously we saw a crest meeting a crest, and that caused reinforcement, but here we're seeing a trough meeting a trough. One thing I forgot to mention is that when I say that this is A and this is 2A over here, these are distances, not displacements. Okay, so remember in this example here the displacements are negative because they lie below the equilibrium line or position. The final example we're going to look at in this video is what happens when a wave meets its reflection. Okay, so in particular what I'd like you to think about is when the individual waves are at this position here at some moment in time, what would their total displacement be? Just want to point out that this point here of zero displacement for the orange wave is in line with this point of maximum displacement of the blue wave, and similarly this point of zero displacement here is in line with this maximum negative displacement down here. So once again, please pause the video and have a think about what the total displacement would look like. Alright, so it turns out that the total displacement would look like that. Now how do we know that? Well, again, we know that at this point here, call it x, if the displacement of this one is 0, then we're just going to add that to a displacement of a. So that gives us this point over here. Okay, so that's point x. Similarly, we know it will be something similar, pretty much the same kind of story at point y. So we're adding 0 to minus a, which will of course give a total displacement of minus a. Okay, so that's what's going on at point y. What about the point that lies halfway between x and y? Call it z. Well, at z, we know the displacement of the blue wave is going to be a over 2, half a, right? And the displacement of the orange wave is going to be minus a half a. Okay, so if we add a half a to minus a half a, okay, as we should from the principle of superposition, right, the total or net displacement at point z is just going to be 0. So hopefully you can convince yourself that if we were to pick any other point along this axis here and combine the individual displacements, we would get something that looks like this. Now, as the waves continue to move to the right and left respectively, there will come a point in time when they will be individually positioned as shown here. So at this moment in time, the displacements of the two waves will exactly mirror each other. So if the displacement of the blue wave is, say, a quarter a, the displacement of the orange wave at that same point will be a negative quarter a. And of course, if we add those displacements, we'll get a net displacement of 0. And that's going to be the same story for any point we choose. Alright, so again, if we choose this point here of maximum displacement a, the displacement at that point will be negative a. So a plus minus a will again give a total displacement of 0. So here we're seeing a very interesting phenomenon known as the cancelling of waves. This is what happens when a crest meets a trough. More precisely, it's what happens when the crest and the trough have the same magnitude of displacement. So for example, if we had a crest here with a smaller maximum displacement, say it looked like this, then there would be sort of partial cancellation but not complete cancellation. So we wouldn't see 0 displacement. In fact, far from it. So let's just check the simulation to see that what we've just figured out does indeed happen in real life. I'll just pause it there. That's sort of close to the first total displacement we figured out for these two waves meeting, and then we see that at this specific point in time there's zero displacement, a complete cancellation. I just went past it there. And then remember, the waves just continue to do their own thing, and eventually we'll see the shapes emerge again and they go on their merry way. Throughout this video we've been using this simulation of transverse waves on a string or a rope. However, it's really important that you realize that the principle of superposition is a general principle. So it applies to all waves, okay, not just the kind of waves we've been looking at. So in particular, it applies to both transverse and longitudinal waves. So for example, it applies to sound waves, and I'll mention a very nice example of this in a moment. It also applies equally well to other transverse waves, such as electromagnetic or EM waves, including visible light. And there's some very nice and simple, beautiful experiments that show this, and you might have already done some of these. The principle is also applicable to quantum waves. So perhaps you've met the idea of wave-particle duality, which states that elementary particles such as electrons, under some conditions they display wave-like behavior more than particle-like behavior. And the principle of superposition explains very nicely kind of what goes on in such scenarios. Now, despite everything I've just said, it turns out that the principle of superposition actually doesn't apply to all waves. Okay, so there are more complicated wave phenomena, what are called non-linear waves, for which the principle of superposition doesn't hold. Now, you can look this up if you're really curious. You don't need to worry about it for A level. I'm just pointing it out in the interests of honesty. To finish, I just want to mention a very nice real-world application of the principle of superposition, and that is noise cancellation. So perhaps you've used or you have noise cancelling headphones which cancel out or somehow mysteriously remove the background noise around you. So let's try to understand the basics of what's going on there. So imagine you're trying to listen to some music or a podcast or whatever, but there's some background noise. Okay, so this noise is a sound wave, and that sound wave can be represented as a displacement time graph. Okay, so this is in contrast to the graphs we've been looking at previously, which have been displacement distance graphs. Okay, here we're looking at a displacement time graph because we're interested in the waves or the displacement at a single point or points, namely your ear. Okay, so if the noise has this sort of profile, if it gets picked up by sufficiently sort of clever electrical circuitry, that circuitry can create a mirror image of that noise, and that's represented by the purple wave. Okay, so it's a bit rough, but hopefully you get the idea. So the black and purple waves are just mirror images of each other. And of course, as you probably guessed from what I've got here, from the principle of superposition, if we add these two together, what we get is a total displacement of 0 at all times. So in other words, the noise has well and truly been cancelled, and so what's left over is the music or the podcast or whatever that you're trying to listen to. Let me end by saying thanks to PhET for their wonderful simulation that I've used in this video. I'll provide a link to it in the description and highly recommend you check it out and see what weird and wonderful patterns you can create from superposition. If you found this video useful, please like it, share it, subscribe to the Forest Learn channel if you haven't already, and I welcome any comments or suggestions you might have, so please get in touch. So thank you for listening, and see you next time.